Hello everyone and welcome to another episode of FiST Chat, the vodcast that features discussions on the topics of film, science and technology. My name is Ben Warner and I'm joined by my colleague and hopefully he'd want to travel faster than light with me as well, Steve Kern. How you doing there, Steve?
Hi Ben, yes, it's very exciting, isn't it? The prospect that we could actually travel faster than light. Oh. Who would have thought? Certainly not Einstein.
That's right, strap me up, I'm ready to go to warp speed.
That's it.
So don't forget our website is available at www.fistchat.com. All our social media, YouTube, RSS, MP3s, everything you can think of that we've produced, I think you can access it from that website. And interact with us as well. I'd love to hear from you. We've had a couple of chats with people already, and it's always good to do that sort of thing. We're keen to do that. That's what this forum is all about. So as we alluded to, we are going to be traveling faster than light. So if we're going too fast for you during this episode, just bear with us. It's all good. You can maybe put a pause on there or something, or just run us at a slower speed.
That's right. Although I don't know how much faster than light we could actually travel.
Well, absolutely. I mean, it's a great announcement when you hear something like that. In that, scientists discovered at CERN that. So far, that that these neutrino particles can actually travel faster than light.
Or appear to be. Should say appear to be, Ben.
Or appear to be. Now, that automatically, generates a headline. Einstein's wrong. Throw out the theory of relativity. It's all a load of crap, and it's easy to jump there because you just hear a soundbite like that and you want to jump into it. And I guess from a theoretical perspective, yeah, it definitely throws up some interesting things. But I mean, before I get back to it, it's like the theory of gravity and things like that, where if you get theories that come afterwards that perhaps they don't necessarily supersede it, but they complement an older theory. It doesn't mean, like, say, an older theory is suddenly wrong. It just means that it's still good at explaining certain things. But in this particular case, they found that these neutrinos could travel. I don't know how much quicker it was.
Six
nanoseconds?
By 10 to the minus 9th.
Nanoseconds.
Not 9. So it's 6 nanoseconds, which is, honestly, it's absolutely no time at all for you and me. No time at all in the history of the universe. Look, the reason people are really excited about this, and CERN have gone and checked again, because they have seen anomalies like this before, several times in experimentation, but CERN hasn't been able to find where they've made the error. So what they're saying at the moment is that these neutrinos appear to have travelled faster than the speed of light, very, very slightly. And they've opened it up to the world or the world or other physicists to actually check their data to determine if it's true. Now, before we even talk about what this might mean, the fact that the whole world has jumped on this and got excited about it is because, let's face it, it was the speed limit, the ultimate limit, and really, for all of us who want to go into space, we need to be able to travel faster than light to get anywhere in any decent amount of time. So the mere prospect that it might just be possible to travel faster than the speed of light makes everyone from scientists, even though these physicists won't admit how excited they are, they're being very cautious. They're saying, "Oh no, it's still probably an error," but everyone knows this could be it. If we're going to go anywhere in space, we're going to have to be able to do it faster than light.
Absolutely. But I mean, that sort of cautious behavior is kind of a general thing in terms of scientific discovery anyway, because everything has to be checked, rechecked to make sure that it wasn't some sort of aberration. But
absolutely,
But like you said, it's just an amazing sort of thought. And to me, even though obviously in a theoretical way, this kind of is exciting, like you said, in a practical sense, to the average Joe on the street, it's not actually going to make you go across the other side of the world any faster that you would notice or anything.
In a practical sense, it won't shorten the amount of time you spend waiting at McDonald's. Okay, and really we should probably clarify here: 6 nanoseconds. Okay. On a 4 light year journey to Alpha Centauri, 4 years will still take you at this speed, but you'll get there an hour quicker than light will.
Oh, well, that's always good to get there early, isn't it?
Well, it certainly is. We're talking about very, very small amount of time, which is why it could quite likely be an error. Right. They just can't find the error. I mean, but what's exciting is how are these neutrinos getting here faster? Or how did they make that 750-kilometre journey faster? Is it because they managed to go through the curves in space? They took shortcuts through other dimensions? This is what we're really excited about. And this is where you're exactly right. You know, when Einstein came up with the theory of relativity, you know, Newton's laws, which are the basic mechanical laws of physics, still hold true pretty much. You know, if someone hits you in the head, your head recoils, you know, with equal and opposite force. You know, I think photons being the speed limit are probably pretty much up there. Photons are light. They're both particles and waves at the same time and have no mass. And the reason is, as humans or as beings with mass, that light is, or the speed of light is the maximum limit, as far as we know, is because of the equation E equals mc squared, which is energy equals mass times speed squared, which what that means is the closer you get to the speed of light, the more and more energy you need to get there. So anything with mass, humans or living objects as we know them, organic life, as you can get to 99.9999999% the speed of light, but you would never have enough energy to actually get to 100%.
Right.
Muons, these subatomic particles, the neutrinos, are subatomic. What they're able to do, this could open a whole new door of physics. Very exciting.
No, absolutely. I mean, one thing that this did sort of sound off to me in my head, just in terms of how scientific discoveries work and the way we process them, is that even though, say, like we said, in a practical sense, it probably doesn't mean that much to the man on the street or woman on the street, but it reminds me that just because something we may have believed was, 100% accurate and explained whatever we thought was right, the universe is such a big place that we can't just assume anything anymore. It's the idea that just because something we don't understand or know something now doesn't mean it can't happen. If we're going to go into speculation territory here, I loved, there was another article that I saw where they were talking about if you're starting to go faster than the speed of light, that the idea if you hold up 2 torches and if you, depending on where you are, if you're going faster than light, it might seem like you're traveling back in time when you, because the light will... that sort of stuff. Are we starting to get all that sort of fanciful and all that sort of thing, or is it? What do you think?
I think this is where the physicists are getting really excited. On the one hand, they're terrified that what they've believed for 100 years of modern quantum physics could be overturned, and perhaps they would have to. And we're talking at the theoretical level as well. Exactly as you say, to you and me on the street, probably doesn't matter that much. It would matter to Captain Kirk and Picard on the Enterprise, though, because that's what their warp speed depends on.
Yeah.
So, but the fact is that physics and theoretical physics, and this is obviously experimental physics, what we're seeing here, because actually done it, measured it, works slightly differently to the other sciences. It's all the same in terms of that we observe something, we observe an action, but physics uses mathematics to explain, what they're seeing. And what's really interesting about it is that in our universe, maths holds or seems to hold. It's a set of rules and laws that seem to hold very tightly. So when we go and we see something that's new or different, what the physicists will actually do is look for the mathematics behind that to explain that. And the only way I can really sort of, I guess, explain what that means to ordinary people is in the same way that we use language. You know, we might write down, you know, what it looks like outside on a spring day. Physicists use math, and through that they explain what we're seeing. And that's how they will find these ripples in space and show you that a torch, you know, looks like it's disappearing when it's coming towards you. Yeah, it's truly incredible what we might find if indeed this research turns out to be true, and how it might redefine our understanding of the universe and our exploration of it.
Well, isn't like quantum mechanics dealing with all that sort of thing? Isn't that sort of like a very sort of tricky area to explain, because it's a much more chaotic kind of world when you're looking at things at that level?
It's interesting because as someone who good physicists, you know, explain these things very well. For instance, people tend to think of subatomic particles, protons, neutrons, and electrons as balls. But we can't actually see anything at a subatomic level. They're actually too small. There's no way we could possibly see them. But we could see them. Chances are they would look like waves, like squidgy sort of waves. And yet when we try to pinpoint where they might be with some of the physics they use, we do them as an actual point in time. And photons work the same way. So you're talking about particles that don't behave like anything that you and I know in our physical world around us. So, but I mean, we can't see the curves in space, but we know they're there because we make observations about light or gravity.
Yeah, that's right.
And the way that it travels through space, and we can explain that mathematically. It is very complicated, but you know, if you've ever listened to someone like or read Carl Sagan or listened to people like Brian Cox, who are very eloquent, or Pamela Gay, who's got the astrophysics podcast, great explanations. You know, and they're the sorts of people that can help explain this much better than probably you and I can.
Oh, absolutely. we can just sit here and get excited about the whole about the whole thing.
Absolutely, and I am thrilled, Ben, because forget going to Mars now. I mean, you know, the fact that we could actually travel to some of these planets we're discovering 5, 6, 7, 8 light years away. You know. And of course, I'm sure most people are familiar that if you make that journey, it might only be four light years for you. Yeah. But for the people back on Earth you leave behind, by the time you get back, they'll all be gone because you'll be coming back in Earth time several thousand years later.
Yeah, it's a fascinating thing to think about. It kind of sort of does your head in when you start to think of it in those terms, and how different the universe can work at different levels.
Look, it's amazing. It's an amazing place out there in the universe, and it's huge. I mean, to shave, I think I did the calculations, and do correct me if I've got this wrong, but I think if we travelled to the constellation of Scorpius from Earth, which is 36,000 light years away. If we travelled at the speed that these neutrinos travelled, which the CERN scientists discovered, we get there 1 year quicker in 36,000.
Not terribly efficient, but again, still early.
In the meantime, hundreds of millions of years will have passed on Earth. That's not good for anyone.
No. Oh, well. Yeah, I mean, maybe that's probably a good point to finish up on, because maybe it's hopefully in the next couple of weeks and months we'll find out the actual findings from this particular little project, and if it turns out to be true, then we're in for an interesting time ahead.
Well, anyone with an interest in cosmology or astrophysics will the world will be turned upside down. The universe will be turned inside out. I don't know.
Absolutely.
Tweet us with your thoughts.
Exactly. So don't forget our website, www.fistchat.com. Visit us there for all our episodes. You can catch this one as well, and you'll and interact with us and leave some comments and let us know what you think. That's it for this week's episode. So until next week, we'll catch you then.